Hi everyone, welcome to your first ever flipped classroom video. We're going to be learning about chemical equilibrium today. The goal of these videos is for you to be able to take notes on your printout from the PowerPoint like you usually would in class, and then when you come to class you will do what would normally be considered your homework. So you'll do the homework practice problems that you're supposed to usually do at home in class. And this will hopefully allow everyone to not only get the notes down, but actually do the homework before the tests come up. So you should have your notes in front of you right now. We won't get through the whole packet in this video, but we'll get at least partway through. So let's begin. The concept of equilibrium. So some reactions go to completion, and we use a one-way arrow for that. So for instance, hydrochloric acid, it's a strong acid, and we know if something is a strong acid that it will completely dissociate. So strong acids, ooh, there's my nice handwriting. Hopefully I'll get better over time. Strong acid will completely release all of those hydrogens. And so we have a one-way arrow there. It's not going to go back the other way. However, we also have states of balance, a two-way arrow, and here are some different examples of equilibrium. Static equilibrium, you have an object at rest, things aren't changing. So you could think of this as like a person balancing on a tightrope. They are standing up there, they are balancing, they're not moving, things are not changing, object at rest. Dynamic equilibrium is when there are two opposing processes that are in equilibrium. So we're going to deal with chemical equilibrium, which is a dynamic equilibrium, where the rate of the forward reaction is going to equal the rate of the reverse. Ooh, that is messy. Oh well, you get the idea. Reverse. So this means that it does not mean that the forward reaction is going to stop and the reverse reaction is going to stop. It means that the rate of the forward, so the forward reaction is going to go just as fast as the reverse reaction. They're both still happening. And equilibrium like this will result because the reaction is reversible. So here are some examples of reactions that are reversible. We could have gaseous water turning into liquid water, or we could easily send that liquid water back into the gas state. We could take sodium chloride as a solid and turn it into aqueous sodium chloride, or we could go the other way around. So these are reversible. We also have some examples of biological reactions that are reversible. So here's hemoglobin binding with oxygen in the alveoli, I think I said that correctly, of the lungs, and later on the oxygen is then released back into the cells within the organism. So it goes back and forth, reversible. Here is a graph that shows something that's at equilibrium. So you're going to want to be able to look at this and figure out, okay, where is equilibrium reached? So go ahead and look at your graph right now. You could pause it if you want to think about it for a little bit and try to figure out where is equilibrium reached. I'm assuming that you paused it to think about it. If not, oh well. So equilibrium is reached right, oh, I need to click on the slide. It's reached right there at time equals 60 seconds. And you can tell us because at that point the concentrations stop changing. If you look at the y-axis here, the concentration is 0.2, so N2O4 at 60 seconds stays at a concentration of 0.2. It just continues on at that concentration. And the same thing with NO2, it reaches a concentration of just under 1.6 and it stays at that concentration. The reaction is still going. We are still forming NO2 and forming N2O4. They are just kind of canceling each other out to where you get the same concentrations at all times. Here is another example of equilibrium. So this is also equilibrium. However, in this case, it's showing that your two different substances at equilibrium have the same rate. So what you're going to want to remember is, I'm going to go back to the last slide, To be at equilibrium, something does not necessarily have to be at the same concentration. What they do need is to be going at the same rate. The rate of appearance and the rate of disappearance need to be equal. So how can you tell if something's at equilibrium? Here we've got N2O4, which is colorless, whereas NO2 is brown. You can look at something like this and figure out, oh, I don't know, where is that at equilibrium? I'm not sure. Why don't we just try writing the rate of the forward reaction and the rate of the reverse reaction and show their relationship. So, for example, let's assume that we're back in the last chapter. We're talking about kinetics, and we're going to assume that this is our elementary reaction. It doesn't proceed in steps. So I'll write the rate, I'll write the rate of the forward will be equal to the rate constant for the forward times the concentration of N2O4, and the rate of the reverse is the rate constant for the reverse times NO2. And we know when we write this sort of thing, the coefficients, like this number 2, will become exponents. That's sticking with us during this unit. So we should be able to set these equal to each other because we're saying it's at equilibrium. And when things are at equilibrium, the rates are equal to each other. The rate of the forward is equal to the rate of the reverse. So Kf of N2O4 is equal to Kr NO2 squared. That will become important soon. So, like we've been saying, at equilibrium, the concentration of reactants and products no longer change. And like we just wrote down, the rate of the forward reaction is going to be equal to the rate of the reverse. In order for equilibrium to occur, neither the reactants nor the products can escape from the system. So it needs to be a closed system. We basically need it to be in a tiny little box, or a large box, whatever, but a box where nothing leaves. Nothing leaves. It all stays within the system. So at equilibrium, a particular ration of concentration terms equals a constant. So we're going to have a new constant, a new letter, and you'll probably be annoyed at the letter. It's the letter K, but not lowercase k. Of course not. Why would it be the same as before? It is uppercase K. Remember when I went on that rant about needing to be able to tell the difference between your uppercase and lowercase k's? Yeah, that's coming back. So you want to make sure that you understand the reaction doesn't stop. It does not stop. It's still going. And the equilibrium condition can be reached from either direction. So you could start with your reactants, and your reactants would do whatever they need to do to become the products, and eventually equilibrium will be reached. Or you could start with the products, and they will go backwards in the reaction to form the reactants, and equilibrium will be reached. Very important, very important. The concentration of most species will remain constant, but that does not mean they will all be the same value. You could have different amounts of the reactants than the products, but as long as the whatever those amounts are remains constant, then it's at equilibrium. So here's our equilibrium constant. Again, it's the capital letter K, capital K. For a forward reaction, reactants become products, and here is your rate, basic equation. Rate of the forward is equal to the rate constant, lowercase k, of the forward concentration of the reactants. And for the reverse reaction, you just flip this around. So now the products are becoming the reactants, and here's your rate equation for that. Concentration of the products this time. So we'll set them equal to each other because we know the rates of the forward are equal to the rates of the reverse. And we're going to do some fancy math and solve so that the concentrations are on the same side as each other. So we'll divide both sides by concentration of R. And divide both sides by the rate constant of the reverse. Those go away, and you end up with this. The concentration of the products over the concentration of the reactants is also equal to the rate constant ratio, which is also equal to our new best friend, the equilibrium constant. So here's some information about real life. We have the Haber process, which is a reaction based on the production of ammonia. And this process, some people believe, is the most important discovery in the past, I don't know, many hundreds of years. People find it to be extremely important, and the reason is it keeps us fed. This process allowed people to create ammonia, which is very important for feeding plants. It's basically a fertilizer. And the cool thing is, you can make fertilizer out of air. The nitrogen in the air will react with hydrogen, and it'll form ammonia. Just random information, you don't necessarily have to know this, but nitrogen is held together by triple bonds. And triple bonds are really difficult to break. Looks like this. Let's see here. 1, 2, 3. Oh, no, not there. Oops. Hang on. There. Draw my Lewis structure. There. So nitrogen is held together by these triple bonds, which are really difficult to break. So what happens is they use a catalyst, usually a metal, and under high pressure and temperature, and it allows us to basically pump out ammonia like crazy, which allows us to grow more plants, which allows us to eat our food and stay alive. Woohoo! So here's our reaction. We're going to use it a lot. It's going to be a wonderful example. So nitrogen gas plus hydrogen gas becomes ammonia gas. So here's something called the law of mass action. Here's our generic chemical equation. And we're going to use the equilibrium constant expression, Kc. When it has the letter C like that, all it means is we are basing our equilibrium constant off of concentrations. We don't always base it off of concentrations, but if it has the letter C, then it is. And it is equal to, ooh, that looks like a jumbled mess. Let's try to think about it in different words. This is the concentration of the products, C and D, divided by the concentration of the reactants, A and B. C and D are multiplied by each other, A and B are multiplied by each other. And then where are we getting these exponents from? Oh, from our balanced equation. So make sure you're balancing equations. Make sure they're balanced because you need those coefficients. They will become our exponents. Very important. This equilibrium constant expression depends only on the stoichiometry of the reaction. It does not depend on the mechanism. So if you hated reaction mechanisms from the last unit, congratulations. They are not necessarily that important during this unit, although you will want to know them for the AP test. So anyway, the path of these products forming is not important. We just need that balanced equation. So what we're going to do then is write the equilibrium expression for the Haber process and pretend that that answer is not sneakily hiding up here. So I'm going to go back a slide. All right, so we have, you can ignore that. It's, oops, me just messing up. Ignore it. So here is the Haber process. Let's write out our equation. So Kc, we're going to have the products on the top. So if you'd like to try this on your own without me, go for it. Pause. Otherwise, I'm going to go. So we need the concentration of NH3. That is our product. And we have our reactants. Okay, I'm going to treat you like you're in class now. Is there anything wrong with this? Doop-de-doop-de-doo. Yes, something's wrong with it. What's wrong with it? We are missing our exponents, which we get from the balanced equation. So ammonia needs to be squared. Nitrogen, invisible 1. Hydrogen, cubed. And that's it. You did it. And if you look here, you can kind of see it. It's in there. Okay, there are different ways to express K. K like this could mean anything. It could mean anything. KEQ is the generic equilibrium constant. So again, it's generic. It could really mean a lot of things. However, Kc is specific, the equilibrium constant using concentration, whereas Kp is the equilibrium constant used for gases. Gases. And they need to be at certain pressures. So we're plugging pressures into the equilibrium formula. It's basically exactly the same thing, so makes your lives easier. If you see K used, the problem either doesn't care if it's talking about concentration or pressure, or it will tell you, oh, this is talking about concentration or pressure. So again, Kc is in terms of concentration, and to figure out Kc, you need to plug equilibrium concentrations into the expression. We do not use solids and liquids in Kc. We do not use solids and liquids in it. And see if you can figure out why. You could pause if you want to think about it. We know that Kc has to do with concentration. Do we have concentrations of solids? Do we have concentrations of liquids? Can I increase the concentration of water? I can't. These things are already packed as tightly as they can be, and there's nothing else in there. They are pure substances. So these guys don't even have concentrations, which is why we don't use them. You just leave them out. You completely leave it out. It doesn't even show up. We'll go over that in some practice problems. Now Kp is in terms of partial pressure. See if you can remember the name of the guy who came up with the law of partial pressures. If the word or the name Dalton came to mind, then congratulations, you remembered something. So Dalton, and he came up with the total pressure is equal to the sum of all of the partial pressures of whatever gases are in the substance, ... It goes on forever, if necessary. So Kp is in terms of partial pressures, and they are measured in atmospheres. So to figure out Kp, just like Kc, you're plugging in equilibrium numbers, except this time they're pressures, into this expression. So you'll have the partial pressure of the products raised to whatever their exponents are from the balanced equation, divided by the partial pressures of the reactants raised to their coefficients from the balanced equation. So these are not concentrations, they're partial pressures. Okay, so I just ranted about this. Solids and liquids are left out. Do not include solids and liquids. That's a very common mistake that people accidentally make. They essentially have constant concentration. You can't change it. You can't affect the concentration of a solid or liquid. They do not affect the amount at equilibrium. So this is your chance to practice writing out some Kcs. You're going to do this part. So you should definitely pause and try it out yourself, and then unpause and see how you did. So go ahead, go pause. Don't be lazy, pause. Okay. Now I'm going to do them and you can see how it went. So I know I want the products over the reactants. So I will have concentration of O2 cubed over concentration of O3 squared. Here I will have concentration of NaCl squared over concentration of NO squared and Cl2. Whoops, oh, that's not right. Squared. And finally, let's see, these are all aqueous. Can I include aqueous? Yes, I can. I can have a more concentrated or less concentrated aqueous solution, so they do get to be included. Oops, I need my plus. That's a plus symbol. And I will have Ag silver plus. And, oh, I just put that up there for no reason. Ignore this. Oh no, never mind, we're good. I'm just having issues. Squared. Okay, make sure if you paused it and you're checking your answers now, make sure you have all the correct exponents. And now, think to yourself, why are these homogeneous? We know homo means same, and in this case it means same phase. We're looking for things that are in the same phase. So here, oh look, they're all gases. And here, oh, yep, all gases. And here, oh, they are all aqueous, so homogeneous. Nothing too fancy there. Okay, so there are some rules you're going to need to know. These you'll have to memorize. Rule 1. The equilibrium constant of a reaction in the reverse direction, the reverse direction, is the inverse of the equilibrium constant. So if I write the equilibrium constant for something going in this direction, that is equal to K. Then if I want to write the equilibrium constant for it going that way, it will be 1 over K. That is the reciprocal rule, because reciprocal means 1 over. Okay, the equilibrium constant of a reaction that has been multiplied by a number is equal to the original equilibrium constant raised to a power. So this is talking about reactions that have been multiplied by a number. So, for instance, if I'm going to go down here, if I have a reaction like, I don't know, let's have this, my favorite, H2O. I'm going to balance it, so I'll have 2 of those and 2 of those. Okay, so if I have this with an equilibrium constant of K, then multiplying the whole reaction times, I don't know, 4 would lead me to an equilibrium constant of K to the 4th power. Okay, third rule, the equilibrium constant for a net reaction made up of 2 or more reactions is the product of the equilibrium constants for the individual reactions. So that's down here. That's what this is showing us. So if I add together equation 1 and equation 2, I should really get another color going on in here. One second. How about blue? Blue is nice. Blue. Okay, so I have, there it is. That's kind of blue. Anyway, look for the intermediates. Yes, that's right. That word is coming back. Cross out your intermediates. Gone. Actually, you know what? Are these intermediates? It depends. If this is one reaction and these are the different steps, then sure, those are intermediates, but we're talking about 2 different individual reactions, so I'm sorry, my bad, these are not intermediates. I'll cancel out those guys. And these 2 reactions combined together just leaves us with B plus F goes to D plus G. So if I had an equilibrium constant of K1 for equation 1 and K2 for equation 2, equation 3 would be K1 times K2. So these are our 3 different rules. We could have a reciprocal. We could have something that is raised to an exponent, which is the multiplication rule, because we are multiplying. And then if we have multiple different equilibrium reactions and we're adding them together, then we multiply the original equilibrium constants and we get the multiple equilibria rule. Fancy. You need to know those. Okay, so Here are the answers to these questions already, so you'd know you got it right if you get this answer, but we have some practice problems. This would be a really good chance for you to practice doing this without listening to me yammering on. So I would recommend that you pause, get a sheet of paper or find some space on your slides and try out these problems. So go ahead and pause. I'm assuming you unpaused now and you're here for the answers, so let's see how it went. You can skip ahead if you got all the right numbers. So the following equilibrium concentrations were observed for the Haber process. Oh, look, it's back. Fertilizer process. And it's happening at 127 degrees C, and I'm looking through here. Oh, they all happen at 127 degrees C. That's good. And they're giving me all these concentrations, NH3, N2, H2, measured in molarity. So calculate the value of K at 127 degrees Celsius. So I'll go to my next slide, and I will actually do that now. Let me get my paper out so I can do this correctly. Okay, so A. Oh, dang it. Hold on. All right. Okay, I'm ready now. So, A. I want the concentration of the products over the concentrations of the reactants. So for this, it's going to be, let's see, I know it's forming NH3. Remember, we need the balanced chemical equation, so it'd probably be a good idea to look back in your slides and find that. I could write it down, I suppose. So we have N2 plus H2 and H3. I need 2 of those, which means I need 3 of these. Okay, so NH3 is squared, and N2 and H3. It's really important to know these are all gases, so okay, everything's hunky-dory. Now you're going to plug in the concentrations they gave you, so we'll have I don't have room, equals 3.1 times 10 to the negative 2 molarity. And remember, this is squared over N2's concentration, 8.5 times 10 to the negative 1 molarity, not squared, and H2 is 3.1 times 10 negative third m. Oops, what's happening? Ah! Times 10 to the negative third. And that should be cubed. Cubed. Don't forget about that. Very common mistake. Plug this in your calculator. You should get 3.8 times 10 to the fourth. If you hadn't noticed already, you're going to be dealing with a whole lot of times 10 to those. So if you don't know the shortcut using the E key on your calculator, you should learn it. Ask me. All right, step B, calculate the value of the equilibrium constant at the same temperature if the reaction was reversed. If it was reversed, so I'm going to go back here. If something is reversed, I need to use the reciprocal rule, so 1 over K. So let's go back here. This is the reciprocal rule, so 1 over K. This is equal to K. So equals 1 over our number, 3.8 times 10 to the fourth, and hum-de-dum, this should be equal to 2.6 times 10 to the negative 5. Okay, step C is calculate the value of the equilibrium constant for the reaction given by the equation 1/2 N2 plus 3/2 H2, okay, reversible, NH3. Okay, so you have to think to yourself, what the heck did they do to the equation? Compare it to the original. It looks like they divided the whole thing by 2. Divided by 2. Or you could think of it as multiplied by 1/2. Not 1/2 factorial. Be careful. Anyway, so go back. Let's see here. The reaction has been multiplied by a certain number. It was multiplied by 1/2. So I need to use the multiplication rule. It was multiplied by 1/2. That's a good way to think of it. So my K is going to be raised to the 1/2 power. So I'll take my original k from up here. I'll have 3.8 times 10 to the 4th, all of that raised to the 1/2. And you should be thinking to yourself, oh, 1/2, that means like square root. Whatever, it doesn't really matter, but good to know anyway. Raised to the 1/2 power means square rooted. Okay, that's C. And D. Calculate the value of the equilibrium constant at 127 degrees Celsius for, okay, so this reaction looks like it was also multiplied by a number, and that is 4NH3. So this one, it was multiplied by 2. Yes, okay, that took too long for me to figure out. Multiplied times 2. So you want k squared. So take your original number, square it, get 1.4 times 10 to the 9th. Don't be that person that misses points on your tests because you forgot the exponents at the very end, the times 10 to the. Very easy to leave that behind on accident. Okay, so solving for Kp, if you remember, it's the exact same thing, except you're doing partial pressures this time. Same thing. Oops. Same. Just with pressures. So a mixture of hydrogen and nitrogen in a reaction vessel is allowed to attain equilibrium at this temperature. We have all of our different pressures, and oh, look at that, it's the Haber process again. So let's see what that was. That was N2 plus H2. I think we needed 3 of those. 2NH3. Okay, and here are our different pressures. So you could pause it if you want to try and figure this out without me walking you through it. Go ahead and pause. Welcome back. So, okay, I want my, oops, it's not a concentration. I want the pressure of NH3 squared over the pressure of N2 times the pressure of H2 cubed. So let's see here, NH3, where's NH3? Here it is, ammonia. And they're in atmospheres, which is good because they need to be in atmospheres for this process. So unit conversions could come back to haunt you. Make sure you know them. 1 point. Okay, that's squared over N2, which is 2.46 squared, and H2, which is 7.38 cubed. And that should be this. All right, what's next? Solving for Kc. So again, you could try this out without me. So go ahead, give it a shot. Pause it and try it. Okay, now we're back. This one was different than what we've been doing. We have 2 different reactions with 2 different equilibrium constants, and we're figuring out the equilibrium constant for a brand new reaction. So let's see here. We have HF, okay. We have, interesting, C2O4 2 minus, okay. And we have H2C2O4, oh, that switched sides too, and 2F, weird, things are weird. Okay, so let's see. Here's your thought process. I need 2 HFs and I need 2 Fs in my final equation. So I better make sure I'm multiplying this whole thing by 2. So keep track. That means I'm going to have to square that at some point. All right, what else? It looks like the C2O4 2 minus needs to actually be on the other side. So that means I need to flip this baby around, which means, okay, if I do the reverse reaction, I need to use what rule if I'm reversing it? If I'm reversing it like that, I need to do 1 over. Okay, oops, not that letter, KC, 1 over. Okay, so these are reversed. So if I were to reverse this, I'll just rewrite it so we can see it clearly. 2HF 2H plus 2F minus, I'm reversing this thing, so here is C2O4, 2 minus, plus 2H plus reversible H2, C2O4. Okay, I want to cancel things out that need to be canceled out. Alright, I will add my two reactions together, and look at that. 2HF, C2O4, C2O4, 2F minus, HCC2O4, HCC2O4. Great. And when I add two equations together, I'm going to go back to this in case you forgot. If you add two of them together, you have to multiply those rate constants together. So that's an evil question. It used all three of our rules. So that means I need to take Kc from that reaction and multiply it times the Kc of that one, except it's not the regular Kc. This one's been squared, and that one's 1 over. So I will do 6. Oops, I don't like blue. I mean, I do like blue. 6.8 times 10 to the negative fourth. This should be squared because we multiply this whole equation times 2. Then I'm going to multiply that times 1 over 3.8 times 10 to the negative 6. And that's 1 over because I flipped this equation around because I wanted to be able to add these together to get that. Plug this in your calculator. That should be your answer. Have you noticed that we're not using units? That's right. We'll talk about that. Okay, this is, we're almost done. Converting between Kc and Kp. So you can actually convert between the two. And it involves PV equals nRT. That should be ringing a bell in your mind right now. This is also known as the ideal gas law. And we can rearrange it to solve for pressure, nRT over V. And we know N over V. N is in moles. Oh, it's over there. And volume is in liters. So moles over liters is also known as molarity. So what we're going to do then is say, okay, in this equation, I'm going to replace that with concentration. And then I'm going to say, okay, well, what if I don't know the pressure and the concentration? If instead I know the equilibrium constants for each? So you could actually have this equation, this handy-dandy equation. And remind me in class to see if this is on the formula sheet. Formula sheet? I don't remember if it is. Because if it's not, you're going to have to memorize it. So we need to figure it out if it's on there. The R we're going to use, I know R is given. We're going to use this one because it's dealing with atmospheres, and our partial pressures are always in atmospheres. Okay, so these things are all familiar to you by now. We can find Kps, we can find Kcs, Rs are given, temperatures are given. However, delta N is new. Delta N represents the change in moles of gas in a balanced equation. So for instance, in our Haber process, we had N2 plus 2, wait, am I getting that right? I don't remember. No, that's wrong. 3H2 and 2NH3. Okay, so here, these are all gases. Gas, gas, gas. So let's count. How many moles of gas do I have on the reactant side? I have 1, 2, 3, 4. I'm just counting up the coefficients. And on this side, I only have 2. So I'll kind of put this in the equation here. I have 2 moles of gaseous products minus the 4 moles of gaseous reactants. So my delta N here would actually be negative 2. So finding delta N isn't actually that difficult. You just have to make sure you have the balanced equation and that you're only looking at gases. Okay, so for the Haber process, we're given Kc at some temperature, and we're going to calculate Kp for the reaction. So get that equation out. Here it is. Kp equals Kc times, okay, write it down. Still working out the kinks here. So we have, oh, where is it? Kp equals Kc times RT to the delta N. I will plug in my Kc, 9.60, and R, we know we're using 0.08, 821, we're always using that one, times our temperature. Now think to yourself, do we use Celsius ever? Basically not. In this situation, again, we're using Kelvin, so plus 273. And if you want to know why, think about the units of R. Liter, atmospheres per mole, Kelvin. Kelvin, 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 Kelvin. So 573. And this is raised to the delta N, which we just figured out. Here it is. -2. And it's -2 because we're saying, oh, we've got 2 moles of gaseous products minus 1, 2, 3, 4. 4 moles of gaseous reactants. Raised to the -2. And if you plug that in your calculator, I sincerely hope this is the number that pops out. So, where are the units? They're very complicated in this sort of thing. It's related to thermodynamics and different activities in quotation marks, which use reference concentrations and pressures that then use ratios that end up canceling units out, and it's very complicated. Don't worry about it. The units get canceled out. That's all you need to know. The units get canceled out. All right, so then, here we have a heterogeneous equilibria. So like we said before, if they're all in the same phase, so like they're all gases, gases plus gases react to gases, that's homogeneous. However, if you have a if you have a solid reacting with aqueous solutions, this is not homogeneous. We have a solid mixed in there. It's heterogeneous. So again, I've said this before, whenever a pure solid or a pure liquid is involved in a heterogeneous equilibrium, its concentration is not included in the expression. You just leave it out. So here we go. I will write my equilibrium expression. I'll do Kc is equal to, actually, you know what? I'm just going to say K is equal to my products. Okay, those are both aqueous, so I can include them. Pb Cl minus. And there's 2 of them, square it. And, oh, it's a solid, so actually nothing goes down here. Nothing. Nothing at all. So it's just this. That's it. You're done. I like these ones. Less writing. Okay, so here are some examples. Here we have lead chloride react plus with water reacts lead chlorine. Okay, cool. Or chloride. Actually, it has a charge. This is referred to as KSP because we only have let's see, how could I say this? We don't have anything included from the reactants. We just have a numerator. There's no denominator. It's just 1. So that's KSP. Doesn't really affect how you think about the problem too much. Just know that KSP is just another equilibrium constant when we're not including our reactants because they are all solids and liquids. Let's see here. So we have equilibrium between solid salts and it's that doesn't need an apostrophe. It's ions in solution. So there is no denominator because we don't include these because we cannot change the concentration of a solid or a liquid. Here's another example. We have hydrofluoric acid, water, hydrogen, and fluoride. And we have something called Ka. So again, exact same thing as before, except we're dealing with acids, so we'll just put an A on there just so we know we're working with acids. Notice how water is left out because, hey, it's a liquid. Don't include it. This one has wrong in big red bold letters. We are not going to write an equilibrium constant for this because it has a strong acid. Hydrochloric acid is a strong acid, which means they don't reach equilibrium. It just completely falls apart. All the hydrogens are released. It's not reversible. So you do need to know if something's a strong or a weak acid. So let's look back here. HF. Is hydrofluoric acid a strong acid? No, it's not. It's weak. It's weak. It's very scary, but it's still weak. So we can write a Ka. Just means we're doing this with an acid. All right, last 2 slides, then we're stopping. Magnitude of equilibrium constants and what K tells us. So you're going to want to know how the magnitude, so the size of the equilibrium constant, affects what's going on. So if K is much greater than 1, if we have a large K value, then the equilibrium lies to the right, which means we have lots of products. This just basically means lots of products, not very much reactants. So it gives us a big number. If we have a very, very small K, less than 1, not negative, less than 1, then our equilibrium will lie to the left. We have not very many products, and we have lots of reactants. And these values can change with temperature. So here, looking at this one, is this large or small? Hopefully the word large popped into your head. This is a large number. It's much greater than 1. Greater than 1. Those aren't 7s, it's greater than, sorry. So that means that equilibrium lies to the right. It is product favored. These are really bothering me. They're greater than symbols. Okay, last slide. So you're going to try this out yourself. You're going to try to figure out, is the value of the equilibrium constant for this scenario greater than, less than, or approximately 1? So you have to imagine, all right, this represents AB. This is going to represent B, and that'll represent A. So go ahead and pause it. See if you can figure it out. And I'm looking at this and I'm saying to myself, wow, there sure are a whole lot of ABs. Look at that. Oh my gosh, there's so many of them. It keeps going forever. So it looks to me like the concentration of AB is way higher. And this is a reactant. That's a product. So that means that I'll have little tiny product over big giant reactant concentrations, which means I'm going to have a fraction that's very, very small. So this is going to be a K value that is less than 1. Less than 1. And if it's less than 1, that means it is reactant favored. Okay, that's it. You made it through. I hope you enjoyed. If there's something you're confused about, here's the nice thing about videos. You can just rewind it and see how I said it back then. And if it still doesn't make sense, then come to class with questions. You could have written questions all over this packet and come to class with them. I would highly recommend that you print out the first 2 homework assignments on Canvas and bring those with you. Otherwise, you're going to be staring at your phone or like my tiny little projections up on the document camera. Anyway, hope you enjoyed. I will see you later. Bye.